Good day, welcome to another video where we will be talking about electromagnetic waves and electromagnetic radiation. I will be one of your hosts. I am Rainer Abad.
Genesis M. Cruz.
Maria Carmela G. Jamampo. Without further ado, let's get to our topic.
Electromagnetic waves. EM radiation is a form of energy propagation where photons with both particle and wave-like properties travel at the speed of light that makes up EM waves. Examples of EM radiation include radio waves and microwaves, as well as infrared, ultraviolet, gamma, and X-rays. Some sources of EM radiation include sources in the cosmos, like the sun and the stars, radioactive elements, and manufactured devices. EM exhibits a dual wave in the particle nature. Radio waves are electromagnetic waves simply because they are made up of an electric and magnetic field. The magnetic field is an invisible force field produced by a magnet, such as conductor when current is flowing through it. The strength of a magnetic field produced around the conductor, such as a wire or an antenna, is expressed mathematically as this, where H is magnetic field, ampere turns per meter, and D is equals to distance from wire in meters. Electric fields are also invisible force fields produced by a difference in voltage potential between two conductors. Electric field strength is expressed mathematically in this, where E is equals to electric field strength volts per meter, Q is the charge between conductors in coulombs, and E is equals to permittivity in farads per meter, and D is equals to distance between conductors in meters. Power density and field density. Electromagnetic waves represent the flow of energy in the direction of propagation. The rate at which energy passes through a given surface area in free space is called power density. Field intensity is the intensity of the electric and magnetic fields of an electromagnetic wave propagating in free space. Electric field intensity is usually given in volts per meter, and magnetic field intensity in ampere turns per meter. Mathematically, power density is expressed in this, where P is equals to power density in watts per meter squared, E is equals to RMS electric field intensity in volts per meter, and H is equals to RMS magnetic field intensity in ampere turns per meter. The characteristic impedance of free space. The electric and magnetic field intensities of an electromagnetic wave in free space are related to the characteristic impedance or resistance of free space. The characteristic impedance of a lossless transmission medium is equal to the square root of the ratio of the magnetic permeability to its electric permittivity. Here is the mathematical expression of the characteristic impedance of free space, or Z sub S. Electromagnetic waves are waves that can travel not only through air and solid materials, but also can travel through vacuum of space. These waves are electrical energy that has escaped into free space. Unlike mechanical waves, where it is caused by disturbance or vibration in matter, EM waves are caused by disturbance or vibration between an electric field and magnetic field. A changing magnetic field will induce a changing electric field and vice versa. Unlike mechanical waves, EM waves do not require a medium to propagate, hence its characteristics. EM waves travel in a straight line at approximately the speed of light. James Clerk Maxwell, a Scottish theoretical physicist, developed the scientific theory to explain electromagnetic waves, in which he noticed that electrical fields and magnetic fields can couple together to form electromagnetic waves. He summarized this relationship between electricity and magnetism into what are now referred to as Maxwell's equations. Fast forward later, Heinrich Rudolf Hertz, a German physicist, applied Maxwell's theories and the first to generate and detect EM waves in the laboratory setting. His experiment with radio waves solved two problems. First, he had demonstrated in the concrete what Maxwell had only theorized, that the velocity of radio waves was equal to the velocity of light. This proved that radio waves were a form of light. Second, Hertz found out how to make the electric and magnetic fields detach themselves from wires and go free as Maxwell's waves, known as electromagnetic waves. Polarization. The polarization of a plane electromagnetic wave is simply the orientation of the electric field vector in respect to the surface of the Earth. Polarization is important in wireless communication systems. The physical orientation of a wireless antenna corresponds to the polarization of the radio waves received or transmitted by that antenna. Thus, a vertical antenna receives and emits vertically polarized waves, and a horizontal antenna receives or emits horizontally polarized waves. The best short-range communications is obtained when the transmitting and receiving antennas have the same polarization. The least efficient short-range communications usually take place when the two antennas are at right angles, for example, one horizontal and one vertical. Over long distances, the atmosphere can cause the polarization of a radio wave to fluctuate, so the distinction between horizontal and vertical becomes less significant. Wave attenuation and absorption. Free space is a vacuum, so no loss of energy occurs as a wave propagates through it. As waves propagates towards free space, the waves spread out in a spherical way, and this is called attenuation or spaced attenuation or wave attenuation, which results to a reduce in power density, and in real-life applications, the signal becomes weaker. Attenuation occurs in free space and in the Earth's atmosphere. Since Earth's atmosphere is not a vacuum, it contains particles that can absorb electromagnetic energy. This type of reduction power is called absorption loss, and does not occur in waves traveling outside Earth's atmosphere. Mathematically, wave attenuation can be expressed in this. It is generally expressed in terms of the common logarithm of power density ratio in decibels loss.
In Earth's atmosphere, ray wavefront propagation may be altered from free space behavior by optical properties. The optical effects are namely refraction, reflection, diffraction, and interference. Using rather unscientific terminology, refraction can be thought of as bending, reflection as bouncing, diffraction as scattering, and interference as colliding. Refraction, reflection, diffraction, and interference are called optical properties because they were first observed in the science of optics, which is the behavior of light waves. Because light waves are high-frequency electromagnetic waves, it stands to reason that optical properties will also apply to radio wave propagation. The first optical property that we will tackle is refraction. Refraction is sometimes referred to as the bending of the radio wave path. However, the ray does not actually bend. Electromagnetic refraction is actually the changing of direction of an electromagnetic ray as it passes obliquely from one medium into another with different velocities of propagation. Reflect means to cause or turn back, and reflection is the act of reflecting. The second optical property, electromagnetic reflection, occurs when an incident wave strikes a boundary of two media or some or all of the incident power does not enter the second material. The waves that do not penetrate the second medium are reflected. The third optical property is diffraction. Diffraction is defined as the modulation or redistribution of energy within a wavefront when it passes near the edge of an opaque object. Diffraction is the phenomenon that allows lighter radio waves to propagate or peak an outcomer. Interfere means to come into opposition, and interference is the act of interfering. Radio wave interference occurs when two or more electromagnetic waves combine in such a way that system performance is degraded. Electromagnetic waves traveling within Earth's atmosphere are called terrestrial waves, and communications between two or more points on Earth is called terrestrial radio communications. Terrestrial waves were influenced by the atmosphere and the Earth itself. In terrestrial radio communications, EM waves can be propagated in several ways, depending on the type of system and the environment. EM waves travel in straight lines except when Earth and its atmosphere alter their path. Essentially, there are three ways of propagating electromagnetic waves within Earth's atmosphere: surface wave, space wave, and sky wave propagation. Each of the propagation modes exists in every radio system. However, some are negligible in certain frequency ranges or over a particular type of terrain. At frequencies below approximately 2 MHz, surface waves provide the best coverage because ground losses increase rapidly with frequency. Sky waves are used for high-frequency applications, and space waves are used for very high frequencies and above. A surface wave is an Earth-guided electromagnetic wave that travels over the surface of the Earth. As a surface wave moves around Earth's surface, it is accompanied by charges induced in the Earth. The table lists the relative conductivity of various Earth surfaces. From the table, it is apparent that the best surface wave transmission occurs over seawater and that the highest degree of attenuation is over jungle areas. Attenuation over all types of terrains increases rapidly with frequency. Extremely high losses make it impractical to use surface waves for a long-distance transmission of high-frequency electromagnetic waves. Surface wave propagation is commonly used for ship-to-ship and ship-to-shore communications, for radio navigation, and for maritime mobile communications. Surface waves are used at frequencies as low as 15 kHz. What are the advantages and disadvantages of surface wave propagation? The advantages of the ground wave propagation are as follows. Given enough transmit power, ground waves can be used to communicate between any two locations in the world, and ground waves are relatively unaffected by changing atmospheric conditions. The disadvantages of surface waves are as follows. Ground waves require a relatively high transmission power. Ground waves are limited to very low, and medium frequencies requiring large antennas. Ground losses vary considerably with surface material and composition. Space wave propagation of electromagnetic energy includes radiated energy that travels in the lower few mass of Earth's atmosphere. Space waves include both direct and ground-reflected waves. The radio horizon is greater than the optical horizon by about 1/3 due to refraction of the atmosphere. Reflections from a relatively smooth surface, such as a body of water, could result in partial cancellation of the direct signal, a phenomenon known as fading. Also, large objects such as buildings and hills could cause multipath distortion from any reflection. Electromagnetic waves that are directed above the horizon level are called sky waves. Typically, sky waves are radiated in a direction that produces a relatively large angle with reference to the Earth. Sky waves are radiated toward the sky, where they are either reflected or refracted back to the Earth by the ionosphere. Because of this, skywave propagation is sometimes called ionospheric propagation. HF radio waves are returned from the F layer of the ionosphere by a form of refraction. The highest frequency that is returned to the Earth in the vertical direction is called the critical frequency. The highest frequency that returns to the Earth over a given path is called maximum usable frequency. Because of the general instability of the ionosphere, the optimum working frequency is equal to 0.85 MUF is used instead. Almost all HF propagations and nighttime long-distance MF propagation is by skywave. Above 30 MHz, waves are more likely to penetrate the ionosphere and continue moving out into space. Ionosphere is most dense during the time of maximum sunlight. In general, the lower the frequency, the more easily the signal is refracted. In the UHF and SHF bands, a very small percentage of the wave's energy is refracted back to the Earth. Under the best conditions, the maximum distance of a single hop is about 2,000 miles.
Next, we will talk about the terms and definitions in propagation, the free space path loss and how to get it, as well as the fading and the fade margin. So first, let us define critical frequency and the critical angle. Critical frequency is the highest frequency that can be propagated directly upward and still can be returned back to Earth by the ionosphere. Next, the critical angle is the maximum vertical angle at which it can be propagated and still be returned back by the ionosphere. Next, we will differentiate the maximum usable frequency or the MUF from the optimum working frequency or the OWF. Maximum usable frequency is the highest frequency that can be used for skywave propagation between two specific points on Earth's surface. So, in getting the MUF, where it is a limiting frequency for skywave propagation, however, the maximum usable frequency is for a specific angle of incidence. So mathematically speaking, you can see from your screens the formula for the maximum usable frequency. So next, let us define the optimum working frequency. Let's talk about it. Because of the general instability of the ionosphere, the highest frequency used between 2 points is often selected lower than the MUF. It has been proven that operating at the frequency of 85% of the MUF, it provides more reliable communication. This frequency is called the optimum working frequency. At the frequency of 0.85 of the MUF, it is the optimum working frequency where it provides reliable communications. So, next, as you can see from the figure, we can see the frequency from the Earth's surface propagated to the ionosphere and then refracted back to the Earth's surface. So, as you can see, there is the radiation angle. Also, you can see the skip distance. So, what is skip distance? Let's talk about skip distance and skip zone. Skip distance is the minimum distance from a transmit antenna that a sky wave at a given frequency will be returned to Earth. So, skip zone is the area between where the surface waves are completely dissipated and the point where the first sky wave returns to Earth. Is called the quiet or skip zone because the area where there is no reception, because as you can see from the name itself, skip and some skip zone, or sometimes called the quiet zone, because there is no reception happening in that area. Let's talk about the free space path loss. Free space path loss is often defined as the loss incurred by an electromagnetic wave as it propagates in a straight line through a vacuum with no absorption or reflection of energy rather from nearby objects. Simply, in free space path loss, there is no energy actually dissipated. So, it is also a fabricated engineering quantity that evolved from manipulating communication system linked budget equations into a particular format. So next, you can see the mathematical equation for the free space path loss. That's how you can get the free space path loss. Let's talk about the fading and fade margin. Defining fading, it is the phenomenon where their reflections from a relative smooth surface, such as body of water, could result in partial cancellation of the direct signal. This phenomenon is called fading. So, next, the fading margin. Fading margin is the loss to accommodate temporary fading. The fading margin or the fade margin is added to the normal path loss. As I said earlier, it's like what I said earlier, to accommodate temporary fading. For us to get the fade margin, here is the formula for it. Fade margin is equal to the multipath effect plus the Terran sensitivity minus the reliability objectives minus the constant. So here is a sample problem. Determine the fade margin for the following conditions. Here is the given. Distance between sites D is equal to 40 kilometers. Frequency is equal to 1.8 gigahertz. Smooth terrain, humid climate, and a reliability objective at 99.99%. So, substituting the values, the fade margin is equal to 30 log 40, the distance, plus 10 log times 6 times 4 times 0.5 times 1.8. 6, 4, and 0.5 are constants. So, 1.8, as you can see from the given, minus 10 log, 1 is constant, 1 minus 0.999, it came from the 99.99%, minus the constant 70. So, simplifying, 48.06 plus 13.34 minus negative 40 minus 70 gives you 31.4 decibels. That's how you get the fade margin in a unit in dB. That's it. Thank you.